Welcome everyone to the seventh lecture of Maps and Models. And today we are going to talk about vectors. And as a beginning, I would like to show you this diagram that kind of show the spiral. It's a kind of spiral that jumping between maps and models, and this shows the pipeline we are going to pass through through our experiments. So we start with some a map, for example, the geolocation, and then we collect tweets, and then we convert these tweets, images, and text into certain numbers. So we jump to the maps again, and then we use these certain numbers to train a self-organizing map. And then from the self-organized map, we can do a kind of predictions or clustering, which let us go back to numbers again. And then eventually we use these numbers to make renderings and to show our results. So this is a kind of a spiral way of looking. And then if we flatten it down, this is how it looks like. We showed this in the last lecture. And then if you see this red box, then this is, oops, what happened? This is where we are in this lecture. And so today we are going to introduce vectors. So it is the kind of platform or tool or the path that allow us to manipulate what we have through the crawling process. So let's start. So vectors. So vector is a list of numbers as we learned in maybe high school. So for example, this is what, let me just adjust this window to somewhere else. So this is what we learned before. So for example, in on the left is a two-dimensional example. So you have two numbers, 2 and 3. And then these kind of vector can be generalized to any dimension. We call it to n-dimensional Euclidean distance. So it depends on how many individual numbers you have. You have a different dimensional vectors, and then we can calculate the magnitude, or in some other terms they call them length or norm of a vector. So basically it's the square root of the sum of the square of all the elements of the vectors. This is what we are familiar with. And also in geometry, vector representing the direction from one point to the other, and then we can make additions, subtractions between vectors. And then for Cartesian coordinate systems, we can use a vector to represent a coordinates of a point. So this is what we know. And so among all these, we would like to let's say emphasize Euclidean distance, that between 2 points in Euclidean space. So this is actually a quite important part that we, when we are operating with vectors. So assume that we have 2 points in n-dimensional Euclidean space, and then with vectors we can calculating the kind of distance, surface distance between these 2 points. So what we do is we do subtractions between the coordinates of these 2 points. Then we have a directional vector, and then we calculate this norm or the length of this directional vector. Then we get the distance between these 2 points. So why this is quite important, I will introduce in the following slides. And then so basically this is kind of very important operations we need to have with vectors. Yeah, and then the second would be feature vector. So in the context of machine learning, what we have, I think we've introduced a lot about machine learning in the previous lectures. So in the context of machine learning, vectors are also called feature vectors. So because each of these values corresponds to some features, and then here I can make a very simple example. So for example, on the left, we have an apple. So considering how we can describe an apple, we can say, okay, we have color, we have size, we have weight, we have, for example, how sweet an apple is. And then for each category, for each property, we can use certain numbers to represent its property. For example, we can say, okay, 0 is red, maybe 1 is blue, and then in between is some color that between red and blue. And then size, of course, we can say the diameter is 12 or 13 centimeters, and then weight in the same sense. And also sweetness, maybe 0 is not very sweet, 1 is okay, 2 is very sweet, and so on and so on. And also for a person, we can describe it, for example, by the sex, by age, by weight, and also by height, and also something else. So basically we are describing an object using certain properties, and then each property can be there's a value can be used to represent each property. So basically, and then the collection of all these properties, we treat it as an feature vector, which is the numerical representation of an object. And come back to the Euclidean distance. So with using feature vectors combining with Euclidean distance, we actually have let's say a platform that we can compare objects numerically. So for example, we have 2 apples, and then we can compare these 2 apples regarding the 4 properties I've been showed. So we can let's say we have 2 apples that have different feature vectors describing them, and then we can calculate this Euclidean distance between these 2 feature vectors, and then we get a number, and assume that now we have a third apple, and then we can do the similar operations between the third one and these 2, and then we also get another 2 numbers, and then by comparing how large these numbers we get, we somehow numerically know that which 2, for example, are close to each other, which means which 2 are more similar to each other than to the others. So this is why this is basically how feature vectors works. How Euclidean distance works between feature vectors, and with this distance we can actually start to for example, doing predictions. For example, we can say, okay, let's use the one in our data set that has the minimum Euclidean distance to the inputs I have, and then maybe this object that corresponds to the minimum distance will be the predictions I want, for example. And also in the next lecture, when we are talking about self-organized map, so the training and prediction process also involves the calculation of Euclidean distance. So basically, this one gives you an idea how it works with feature vector. And also another important, let's say, operation we can make with feature vector is that there are certain operations allow us to let's say cross dimensionality. So for example, on the left, it shows a very simple matrix multiplication that a 2-dimensional vector multiplies with 2 by 3 matrices, and then the result is a 3-dimensional vector. So and then this operation does not necessarily to be matrix operations, matrix multiplication, it can be any. And then the idea is, I mean, the idea is not to focus on these operations, but to have a feeling that, or an idea that actually we are able to jump in from between certain dimensionality. So for example, on the right, it will be a very simple case that again, we have an apple described with certain properties. Actually, with some operations, we are able, or conceptually, we should be able to predict, for example, what is the price of this apple, and then how do I like it regarding this apple, for example. And then in this case, we are jumping from a 4-dimensional case to a 2-dimensional space. And then actually from how many dimensions to how many dimensions we are jumping is basically depends on our own questions and then what kind of data we are operating, and then it's a kind of flexible thing. So yeah, but then the idea of that we are able to jump, it's another, let's say, core idea within these experiments. Yeah, and then before we are going to talk, before we are talking further, actually, I would like to go back to the concept of map and models using feature vectors. So basically, I would like to say that all the features we've been introducing belongs to the model side, and then all the values for each features will belongs to the map side. So because as we introduced in the previous lectures that every time so in the center is the object that is kind of inaccessible, and then we use models to do certain abstractions on top of it, and then using maps to numerically represent what we already have. And then therefore conceptually these features will be an abstraction on top of these objects, and then these numbers are the results that we get using certain methods. For example, how to measure the color, or how to measure the weight, for example. And then with different apples, then we have the same features with different values, which means we get a map of objects. And also, if we actually, these images here are also a model, correspond to pixel values, which is a map, and then this map is obtained by a digital camera, for example. And so, why let's say talking these concepts again? So because actually in our experiments we are not operating on real objects. Let's say we are operating on digital objects, which means they are already a kind of map, and then we are making models of this already existing map. So because what we have through our experiments, what we are focusing right now are the images and text that we are collecting from the web, or specifically we are focusing on tweets. And then the tweets itself is already a model that talks about the words. So they are written by the users. They are taken by the digital cameras. They are converted into pixel values, and then the integers that represent each characters that so basically the text and the images are all represented in a numerical way, and then rendered in different formats. And then what we are doing here is actually making another level of abstraction or operation on top of these digital objects. And so with feature vectors for digital objects here, the idea is that for example, in the case of images, the idea is that on top of what we already have, which is pixel values, we can treat these pixel values in different ways. So the most simple way will be simply render them as they are, using the same order they've been placed in the memory. For example, one pixel after the other, and then we render it in a similar way. Therefore, we get a colorful image we can read, or we can apply certain operations on top of these numbers. For example, objects detections or edge detections on this image, and then we get something else. For example, the percentage between edges and the non-edges pixels within, let's say, a 16 by 16 area, and then we can divide this image into many 16 by 16 areas, for example, and then we count these numbers. Then we get something else, or we get the probability these objects having different, of this image having different kind of objects, and then we use these probabilities, collect them, and then represent them into a feature vector. So these are the different kind of operations or way of treating these image values we can do, and then the result is another collection of numbers. And then, since the images are already numbers, and why it is necessary we need to do this again, that we need to make another kind of abstractions or to calculate some new numbers on top of them. So I would like to explain this through this very simple case. So let's assume that we would like to let's say separate images based on what they are showing. For example, if they are showing interior spaces or exterior spaces of buildings, and then I have these three images, and then therefore, so conceptually, the left two images should be closer to each other because they represent different places, of course, but then they are all interior space, and then the one on the right representing exterior spaces. Therefore, in this experiment, it belongs, the one on the right belongs to another group. But if we don't do anything and simply use the pixel values, for example, as the code I'm showing here in Mathematica, if we calculate the Euclidean distance of the pixel value of the image, then this is something we get. So the first two images, the result, the Euclidean distance is around 21, and then the first and then the value between the first and third images are 16, and then the same value between the second and third image is 19. So what does this mean? Which means actually the computer tells us that it thinks the second and third images are closer to each other than the first and second, for example, which means it is not the result that we want. So I think this is a quite clear example that tells us sometimes we can't get the actual result we want simply through colors, and then we need something else to, for example, we need to detect if this image actually represents interior space, for example, which means we need another level of operations. And then similarly, when we go back, when we are talking with text, it's make no sense that we compare two texts word by word. So maybe the two texts are talking about the same thing, but in a different way of saying. And then if we naively compare them word by word, which is kind of similar, comparing images pixel by pixel, we don't get very good results. And then therefore, this is why we need to calculate certain numbers to convert these, for example, pixels and then text into some other numbers so that they become similar. And then feature extraction is the mechanism that how we calculate these vectors. And then here I list a name of different way of calculating these vectors, but then we will not go in, let's say, too detailed to each of these methods because we are not learning algorithms here. We are more on the conceptual level, how to operate this data we have, and then what's the idea of each of these methods. So so I will basically quickly jump through each of them, and then I think you also had these slides, and then on these slides there will be links, hyperlinks that you can click. So for example, for both images and text, we have some classical methods that are non-probabilistic, and then some, let's say, new method or currently state-of-the-art method that are based on probabilistic method or using machine learnings. For non-probabilistic method, for example, we have edge detection. So which means we calculate the difference of a pixel between its neighbors, and then we apply a certain threshold. If the difference is above certain threshold, then we say, okay, here's the edge. And then if not, then it's something else. And then, for example, we have one colorful image on the left, and then after applying the edge detection, we can get something like the one showing on the right. And then after we have this black and white image, we can, for example, cut it by, I don't know, 3 by 3, 5 by 5 grid, so that we get a small patch out of this image. And then we, for example, we can calculate the ratio of white and black pixels between within each patches, and then we get a list of numbers. And then the number of these numbers equals to the number of patches we have. So this will be edge detection. Also, we have Fourier transform. Actually, here I will direct you to multi-dimensional transform. You can also search for Fourier transform in Wikipedia, and basically it is an operations that allows us to go to jump from, let's say, time domain to frequency domain. So assume that we have a one-dimensional signal which shows like a sine wave. Maybe I can find a better, yeah, for example, this one shows like a wave like this. What Fourier transform did is to calculate this. Okay, we are not seeing, oh shit, only the slides. Okay, I will, maybe I do it again. Sorry about that. Yeah. Now it's good. How do I, okay. Yeah, sorry about that. Yeah, by the way, the previous screen was like this. So these are the two pictures. Okay. Yeah. So I think, yeah. What we were. Yeah. So so what Fourier transform did is to calculate, let's say, how much percentage standard sine wave contributes to this signal. Standard sine waves with different frequencies contribute to this signal. You can consider it as, you can consider the signal is the addition of multiple sine waves with different magnitude and frequency adding together. And then with Fourier transform, we get the magnitude regarding, or we can say it's a kind of contribution of different sine waves to our signal we have. And then the similar operation can be done in 1D, which is the signal, or in 2D, which is an image. And then, for example, here, this image shows the sine wave of 2D during the Fourier transform, and then the result we have will be also a two-dimensional result. I think Carla will further explain you when she will do this operation in through code. Also, we have, for example, half transform is it's a method to really fast detect edges and lines and circles from images. And basically, it transforms an original image to some other, let's say, dimensionality, and which you can render it as as an image. And then by detecting the white dots of an image, then we can somehow calculate the position of lines and circles, and also in the case of circles, the position and the radius within the original image. And I will not do a very detailed search, but just to quickly go through it, and also object detection. So now with artificial neural network, we can actually, for example, detect different kind of objects from then photos, and then we can actually, each of these objects are not say either yes or no, but more or less how much confidence the computer has to regarding each object, and then we can and then at the beginning we can have a list of objects that we may interested, and then for each picture we detect these objects and then see how much confidence the computer are regarding each type of objects, and then use this method we can convert an image to a list of probabilistics. And also image captioning, which is techniques that to automatically generate text that describes the image using machine learning as well. And for text, I didn't find too many, but also there are still non-probabilistic method and also probabilistic method. For example, for non-probabilistic, we can do word counting. For example, we have a dictionary of keywords, and then for different text, we can count the frequencies of different keywords, and then we have and then in the end we have a histogram that represent different text. Also, we can have this word to vec model, which is an embedding model that learns the what would be the well, what's the mechanism for this? So it's focusing on the adjacent or neighboring words between natural text. So they first collect this text, a huge bunch of text from Wikipedia, and then they have they focusing on what is the second word shows after the first word, and then they repeat this operation for all the adjacent word within all the text, and then to calculate and then in this way to embed each of the words to a numerical space. And then within this numerical space, words with similar meanings will gain similar coordinates to each other. Also, sentiment and analysis, which is another method that try to estimate if the emotional part of the text, which may, for example, tell us if the text is positive or negative, and then using this information, we can also include this information into our text modeling, so that we have a dimension that represents if the text is positive or negative, for example. And then the last part will be the demonstration with using these feature extraction mechanism on top of the previous collected tweets we have. And then this is what we need to do in today's experiment. So basically, we have to convert all these tweets to numerical representations again, so that we can operate it in with self-organized maps. And of course, I mean, after today's lecture, it doesn't mean that we are stopped crawling data already. So basically, crawling data will continue until we have a lot, and then but in parallel to crawling, we can start to calculate these vectors so that we can begin to play with them. And so here I will show some quick examples, and then Carla will explain each of these in code in detail. So for example, we have images. We can focusing on color as we show on the top. So we kind of resize this image into a very low resolution. For example, maybe 16 by 16 or 32 by 32. Okay. Then I jump it quickly. And then we go to some numbers, and then for edge detection is the same. Also feature extraction will be the same, that we have these different numbers correspond to the probability of different categories. And then Fourier transform. What's happening? Yeah. And then you see that with different input images, we actually get different numbers. They are all calculated using the same method. Yeah. And also text as well, we will show two different ways. One is sentiment analysis, the other is word-to-vec. And for word-to-vec, we will use a pre-trained model that provided by Mathematica. Yeah, so you see with different inputs that the text that the numbers will change. And yeah, so that's the slides part. And then now I will hand over to Carla, and she will show you examples through code.
Well, so before starting with the code, I just want you to go to our website if you haven't and download lecture 7, because in lecture 7 inside you have the code. So I will go to my downloads. I just previously downloaded. We can just do it. So I download lecture number 7. I open, and then the lecture that Google was explaining you is inside this PDF. But if you go inside the folder of code, here you will find the code. So we will open this. So one thing before continue with the code, I wanted to thank you all for uploading to the server the pictures of your crawl data. And one thing that we have to be sure, or that we don't have to forget, is that you cannot extract the images from the folder that were saved, because the folder and the GeoJSON file, they need to be together in order to be accessed with this code. So that's really important. So for example, when I crawl, I crawl my tweets in this folder. And in this folder, you have a folder with this long name that has to do with the query you use to crawl the data. And then you also have a corresponding GeoJSON file. So I will repeat again, because this is very important, that you don't move the images from this folder out, is that you keep the folder with the images here, and then you also have this file all together. So you can have in one same folder many crawl data. For example, you crawl different hashtags, but all of them can be inside one folder. This means that you will use all of them to create one sum. If you want to do different sums or different self-organizing maps from each specific crawl data, then you will have to have many different folders. So for example, here I say, I want to do a self-organizing map of Beijing. So then Beijing will be in one folder. And then this folder, where is my folder? So this folder will be out, for example. And then the same thing with the rest. But if you want to work with all of them together, you don't need to have them apart. They all need to be in one folder. So this is very, very important. Otherwise, the code or the experiment will not work. Okay, so one additional thing we have in this code, so we have this get sample data. So it means if we provide this link if you didn't have the time to crawl your data. But as I saw you all have, so you don't need to use this sample data. This was just for you to work with this code. But today we're gonna work with the crawl data that you have crawled last week. Okay, so we start by opening this slide. And we have the first chapter, which is called How It Works. So I provide, I have two sample data. So I have one image, which is this one. I we'll make it bigger. And I have a sample text also, which is this one. So I'm gonna go step by step on how we are transforming these type of data into numbers again. So what is really important is that you realize when we were talking about, I think it was the first or the second class about anything into anything, meaning that every digital data you have, it has a numerical representation, or it's represented by bits or bytes. So this is how, for example, with this image, you see here, what I'm gonna do first, if I want to work with colors, I'm gonna resize it in a smaller size. So I get kind of a pixelated way of this image. And then I'm gonna ask for all the pixel values of this image. So if you're running this code with me, you just have to do Shift Enter on this line. And then again, if I can make it bigger, I can make it smaller. It just depends how much detail you want to capture with these RGB values. So I'm going to work with 32. So I'm going to resize the image in 32 by 32 pixels, and I'm going to ask the value of each pixel. So you see here, the first top left corner has 0, 0, 0, means it's black, and then while you're moving through the center, you start getting some values. So this is the let's say the normal way how these images are encoded. They are encoded by the color of their pixel values. So one way of encoding is by RGB. So this, we call it RGB vector. A second way that we'll explain you also in the code is by edge detection. So we call this an edge vector. Here, for example, what I'm doing, I'm detecting, you see, I'm detecting the edge of the same image. And we'll just repeat what Hugo said. So how we detect the edge is that when we find a difference between, let's say, we create a threshold, and in this threshold, we see how much difference are in between these two colors that are happening. And then we define this border. And in order to get the value of each, a value of the edge, what we did after detecting these borders, we partition the image in small samples. And then each sample then, here with this function image levels, it's getting the percentage of 0 or white and 0 of each of these patches. So what we're having now is a numerical representation. So I'm going to run this line. Remember, when something is blue, means that it's not run yet. So we have now created the edge list, that is a list of small patches of the same image. And now I'm gonna ask for the image label. So here I'm asking for each of these patches the amount of white and black. And in that way, we are encoding this image that we have from here into a numerical representation that is talking about the edges that it's finding in the image. Another way of encoding images is by this feature extraction of image detection that we'll explain you. So here I also added some hyperlinks, and in the hyperlinks what you will see are, for example, here in GitHub, you have a list of all the algorithms that are used to do this task. So in this specific case, in Mathematica, we are using a specific machine learning algorithm that is called SegNet. And what it's doing is exactly that. It's giving you the probability of this picture to contain these different elements. And then what you, for example, now I'm gonna ask for the elements of this image. So it's telling me in this image, I see a person. It can be maybe a statue. It can be a monkey. It can be a cigarette holder. And I can also ask top probability. Oops. Right. second. So when you want to know how to ask things, you go to the instruction, properties and relation, and then here I said, give me the top probabilities, and then, why? Just a sec. Okay, now it's not working, but okay. So now we have all the elements that are supposed to be happening in this image, and then the one that is more, now I'm asking for all 5 of the ones that are more similar, but if I only ask for, if I only present this image to this function, it will only give me one answer, which is the most probable, that is this person. And what we're doing with this image is, with this, let's say, prediction, is that we are finding this prediction in a numerical space, is a multi-dimensional space, which is giving a numerical representation of this specific category. And this is how we encode the images into a numerical representation that is talking about the objects that are inside the image. And it's not only giving me this one, but it's giving me the probability of all the rest that are not showing here, but it will show you now. So I'm gonna ask for 8 values. So it's telling me like it's less probable to be an orangutan, the one that is inside this image. Okay, so another way of encoding the image data is by Fourier vector. So here what we have, so I make just a small example. So if we ask for the image data of this image, what we get are the pixel values. And it's telling me that if we flatten all these pixel values, we will have 8,000 pixels in total. But if I plot these only the first 1,000 elements, we see that it has let's say a specific rendering. But if I ask the Fourier of this data that we have created here, it's not giving me the same image that we see here, but it's giving me a, let's say, it's transforming from a time domain to frequency domain. So we are seeing that there are some peaks, and in these peaks, most of the information is being recorded. So what we are doing is only getting, instead of having a vector with this dimension, we're gonna cut it in a way that we are gonna get as much information as we can, but with a small sample of this vector. And what we're getting here is that we're not only encoding the color as we're doing with the RGB, but we're also encoding, let's say, the overall of the image. So this is another way to encode the images. And now we are going to do with the text. So for example, we use a pre-trained model that is getting the sentiment analysis of the text, but here it's telling you, it can tell you either it's positive, neutral, or negative, but it also gives you the probability of each of it to be either the 3 categories. So what, instead of only getting the result of positive, we're gonna, the vector will be the probability of each of these 3 to happen. So the text that we saw, I think you can see it quickly, was is an example text. It's called text be or not to be, and then I have 4 examples, and then it says that the first, we have 1, 2, 3, 4, 5, and then here we have that the first is more likely to be a neutral text, the second is a positive one, the third a positive one, and then the fourth is a negative one. And then now I'm just telling you the higher value, but the text will be encoded with these 3 numerical elements. And the last way of encoding text is with word2vec. And in here we are using also, in this hyperlinks, you will see the different algorithms that can be used to, for example, in word2vec, embed the words, so make a word embedding. And what is really interesting with word2vec is that actually you're getting the context of a text rather than just knowing how many words or if you have keywords on the text, but it's giving you a context, an overall context, and it can be compared. You can compare text in this way because you're not comparing word to word, you're comparing the content of each of these texts. And for what it does, each word, it has a numerical, let's say numerical representation that has to do with the location it has in this multidimensional, let's say space. And then each word has a number that then, if it is collected in a list and a vector, multidimensional vector, it gives you a code for of any text, as you see in here. So I quickly explain you all the methods you can use. It doesn't mean that you have to use all of them. It means that you need to be informed what they do in order to choose the right method to encode your data. Because depending on what you're trying to find is how you use the vector. So I just go quickly again, so you can encode your images based on the colors you find inside. You can encode your images based on the edges that the image has. You can encode your images based on the objects that it finds inside, or you can encode your images with a Fourier vector with all the, it's encoding colors and the structure of the image. And in text, you can encode your text based on the content, not the content, but based either it's positive, neutral, or negative, or you can encode your text based on the content itself. So if you have questions now, we can have a short chat. Otherwise, I continue with the code because now we're gonna load the tweets that you have crawled. So if you want to say something, maybe you can raise your hand or no? Okay. So to continue with the experiment, we're gonna import your data. So how we're gonna do it is here, the first line, it does, it creates the path of the working folder. So now if we go here, we go, I'm gonna go to the tweets I have. So I go here, lecture code. So I have these all tweets where I have crawled all my tweets. So now you have to choose the folder where you crawled your tweets. And we continue with the code. So as soon as you have assigned where are your tweets, you run this line. So again, Shift Enter. And here, what you're getting are the ID of the images and the path where this image is located, for example. Now with this line, what we are doing, we are, first we are resizing all the images on a specific size. So all of them should be square. And we are assigning not only, so we are creating we are loading all the images and we are assigning the ID of each image and the path to each of it. So this will take some, let's say it will take around 1 minute. Now I don't have much data, but it's showing me the first 5 elements of my crawled tweets. So here in the following sections, what you see are the different ways of encoding your data. So let's say now I want to focus on the images, and I really don't care about the objects. I only care about how they look. So if I only care about how they look, and not only about how they look, but I want to somehow get the structure, only the structure of the image, I will choose to encode my data with edge analysis. So how to do it? I run this first line. This first line is doing as I show you here, but systematically through all my images. So Shift Enter. It will take some time. I say around 1 minute. It's done, and then I will see my first image, which has this name, is transformed now into this list of numbers. And this list of numbers are talking about edges that are included in my image. So let's say now my question, I realize that I really don't care about the edges, but I do care about the objects that are inside my image. So what I will use then are these feature extraction method, and it's in the same way. So when you, one thing that you have to remember, when you run this line to create the vectors, you need to export them. So remember this to always do when you create the vectors. So you create the vectors and then you export. And when you export, I will show you what I got. Wait, where it is. Here, code, tweets. And I got, you see, I got a new file, which is called back edge. So it creates a file that has the same structure as the JSON files, which contains the ID of the link, but now it's not only containing the image and the name of the image, but it's also containing the vector that we have created. So as I said, it depends on what you are looking for in this data, and depending on the question, you can choose which method to use to encode the images. But let's say, no, I don't care so much about the images. I care more about the text that the users are writing about the specific subject. So then I will use these two different ways of encoding text. So if I want to know either the tweets are talking in either positive, negative, or neutral, I will use this method, so the sentiment analysis. And after creating my vectors, I will export them. Or I care more about the content, what they are talking about. If I can compare different text based on their content, I will use this method. So I'm not going to run all of them. I'm just giving you a quick or a concise and quick example of how am I going to choose to encode my data based on my question. So edge analysis is about the structure, RGB analysis is about the colors of the images, Fourier analysis is about both color and structure, feature extraction on images is about the objects inside the images. These four are, you can use it to encode the images. And these two, sentiment analysis is encoding the text into these three categories, and word2vec is encoding the content of the text. So I'm going to stop now. And as we told you last weekend and on the email, so today you're going to go to work on groups. So we have created these breakout rooms depending on the groups you have chosen to work with. So if you have something to say before going to your groups, now is the right moment. If you have any question regarding what we have explained you, because otherwise we're gonna go into groups now. And Gu and I, we're gonna jump in each of your meetings so we can answer any question, a specific question regarding your project. So the task for the next week will be that you have to create the vectors of your crawl tweets. That's the next task for the next week.
and also keep crawling data if you need. And we recommend you to have a lot of data. So for example, if you focusing on some, let's say before and after coronavirus in different places, and then one thing to focus is the time, and also the other thing maybe different locations, and then we can extend our data crawling in these two things. Let's say one is to go into times, and then the other is to search in different locations, and then try to get more.
Yeah, so it doesn't, what Guo said, it really, you should keep on crawling, because the more you have is better. The more you have, you get more consistent on what you're looking for. And then this vectorization of your data you can always do it. So it doesn't mean that if you do it once, you cannot do it again. It means that in order to continue with the pipeline, we need you to do step by step. But when you master the pipeline, you can do it in one day, the full pipeline.